Hey guys, welcome to this video on the 2018 Level 2 Electricity and Magnetism paper exam walkthrough. So question 1, the candle and the Van de Graaff generator. Sam has connected his school's Van de Graaff generator high voltage DC power source to two parallel metal plates that are 0.08 meters apart. An electric field strength of 2.5 times 10 to the power 6 volts per meter is established between the plates when the Van de Graaff generator is turned on. Calculate the voltage between the plates. Alright, so in this question, we're given the distance between the two plates. Our distance is given to be 0.08 meters. We're also given our electric field strength generated, which is abbreviated by E. E equals 2.5 times 10 to the power 6 volts per meter. And the question is asking you to find the voltage. Alright, so this question, we're gonna look at our formula sheet. We're gonna see that the relationship between these three variables is E equals to voltage over distance. Alright, so we have two out of the three variables, so we can use these two variables to find the third variable. So we can say that 2.5 times 10 to the power 6 is equal to our voltage over 0.08, which is our distance between the two plates. So V equals to 2.5 times 10 to the power 6 multiplied by 0.08. And you should get that your voltage should be equal to 2 times 10 to the power of 5 volts. So that's just 2 with 5 zeros at the end. And that there will be your correct answer, and I'll give you your achieved grade here. So this is an achieve mark here. Alright, the flame of a candle contains both positively and negatively charged particles. When Sam places a burning candle between the two parallel metal plates connected to a Van de Graaff generator, the flame spreads out as shown in the diagram. The negatively charged particles within the flame move to the left, and the positively charged particles move to the right. Alright, so you know from static electricity that opposite charges attract. So if the negative particles are going to move left, that means the left plate must be positively charged. And if the positive charges are moving to the left, then that must mean that our right hand plate would be negatively charged, because opposite charges attract. Alright, so draw the electric field formed between these two parallel metal plates, clearly indicating which plate is positive. Alright, so we know that the left plate must be positive, and we know that our left is positive, so our right must be negative. And we know that electric field lines always move from positive going into the negative, because that's our conventional current. Our conventional current is always the positive to the negative, the current flow. So therefore, our electric field lines are positive to negative. So important things to note down when you're drawing this is that your lines have to be straight. So straight 90 degrees, perpendicular, straight lines. Very important. And you also have to make sure that that your lines are evenly spaced. It doesn't matter what you pick as your spacing distance. For example, if you pick 2 centimeters, then make sure each line is 2 centimeters apart. So keep one thing constant, and that's the distance. That's very important. And the final thing is, don't forget your curved lines. Your curved lines at the end of the electric field. That's to represent that as we get further away, the electric field lines are further apart, which means that they are weaker. Right, so here's I'm just going to use some arrows to represent. Right, so should look something like this. So just make sure your lines are straight and evenly spaced. Alright. Yeah, I'm just doing it roughly, but in the exam you'll have a ruler. So if you have the ruler, just measure out the distance you need. It's very important that you make it pretty accurate so that you don't get penalized. Right now I don't have a ruler, so it might not be very accurate, but I'm just trying to approximate it pretty accurately. Hopefully it's not too far off. It's a bit too much. Alright, that's what it roughly should look like, and don't forget your curved lines at the end of each electric field, so it should look something like this. And don't forget our one at the bottom as well. Alright, and that's what your electric field should roughly look like, okay? Indicate that the left hand side is positive and the right hand side is negative. And this drawing, assuming that including curved arrows, must be perpendicular and equally spaced, that will give you your merit grade. Alright, so this is a merit level question. And to get an achieved, you only have the horizontal line. So to get an achieved, you don't have your curved lines, okay? So if you don't have this and you don't have this, you get an achieved grade there. Alright, next one. Sam then extinguishes the candle, causing a moving trail of smoke to appear. The negatively charged smoke particles travel to the left, and the positively charged smoke particles will travel to the right. An initially stationary negatively charged smoke particle with a charge of 6.52 times 10 to the power of negative 13 coulombs is positioned centrally at point A. The smoke particle is accelerated to the left due to the 2.5 times 10 to the power of 6 volts per meter electric field. Alright, so using conservation of energy, calculate the speed of the 4.5 times 10 to the power of negative 6 kilogram smoke particle the instant before it collides with the left-hand plate, point B, that is 0.04 meters away from point A. Alright, so we have our particle, okay, that's going to be starting at point A, which is here, and it's going to be traveling to the left due to a force of attraction experienced by the left plate. Alright, so in this case, we're going to be finding the electrical potential energy stored, and we're going to use our conservation of energy, the conservation of energy rule, and we're going to say that the EP lost is equal to the EK gained. So therefore, then we're going to use our EK equals to half mv squared in order to find our velocity, okay? Alright, so looking on your formula sheet, you should see that EP is equal to, EQD. That's your electric field strength times of your charge times of the distance traveled. So your EP should come out to be, you know your electric field strength is 2.5 times 10 to the power of 6, so 2.5 times 10 to the power of 6, multiplied by our charge. Our charge is here is 6.52 times 10 to the power of negative 13 coulombs. So 6.52 times 10 to the power of negative 13 times of the distance, which is here 0.04 meters, sorry. And if you plug this into a calculator, you should find that your EP should be, hold up, EP. Sorry guys, just hold up. My calculator. I should get to your EP. It should come out to be 6.52 times 10 to the power of negative 8 joules. Okay, so EP is measured in joules. And now we're going to be using our conservation of energy rules. So we're going to say that EP lost equals to EK gained. Conservation of conservation of energy. And that means our EK is also equal to the EP, which is 6.52 times 10 to the power of negative 8. And we also know that EK equals to half mv squared. Right, so it tells you the mass of that smoke particle is 4.5 times 10 to the power of negative 6, and you also know the EK, so you can find our velocity. Okay, so we know that EK equals to 6.52 times 10 to the power of negative 8, and that's equal to half times of the mass, which is 4.5 times 10 to the power of negative 6, and that's multiplied by v squared, which we're trying to find out. Alright, so basically we're gonna say that 6.52 times 10 to the power of negative 8 times 10 to the power of negative 8 times of the, so you've moved one half, if you move it to the other side, it becomes multiplied by 2. So we're gonna say multiplied by 2 and divided by 4.5 times 10 to the power of negative 6, and then square root of our answer should give us our answer. So we should see that our velocity should come out to be 0.17 meters per second. And that will be your final answer there. And getting your correct final answer of 0.17 meters per second, that should give you your merit grade there. I should put this in red. This is a merit grade up to finding the 0.17 meters per second. To get an achieved grade, you're finding your EP. So if you find your EP here, that will be your achieved grade. Alright, next question. A strong permanent bar magnet is then placed high above the smoke trail, so the North Pole is pointing towards the left. The negatively charged smoke particles are traveling from the candle to the left-hand plate, point A to point B. State 2 changes not involving the magnet that could be made to increase the velocity of the negatively charged smoke particle. Alright, so for these types of questions, so you have to find what can increase the velocity with the variables that you're given. Basically, you can so you know that red pen. So you know that EK equals to half mv squared. You know mass has to stay constant, so that means you can't really increase the mass because it's still going to be that same smoke particle. So you know V is what you're trying to V is what you're trying to increase, and you know that EK, so you're trying to find a way to increase the EK now. And you know that EP equals to EK, so we can say EP equals to EQD. So we're trying to increase the EP, we're trying to find a way to increase that. So as you can see, we can either increase our electric field strength, increasing our charge, or we can increase the distance traveled, okay? Those are just the possible ways we can go. Okay, so let's looking at E. Okay, how we increase E? So E equals to V over D. So we know that E is proportional to V and E is proportional to 1 over D. So therefore we can see that if we increase the voltage that the plate is connected to, we can also increase the electric field strength, and by increasing the electric field strength, we're also increasing the EP, and that's going to lead all the way to our velocity, okay? Or we can, because E is inversely proportional to D, we can say that if we decrease the distance between the plates, that's going to also increase our electric field strength, and by increasing our electric field strength, by linking it all the way back to our velocity, is also going to increase. Okay, so another way. Okay, so that's our electric field strength. We can also increase the charge. Okay, so EP equals to EQD. We can also increase the charge. Okay, so that basically if we're increasing the charge, that's also going to increase our EP, and if we increase our EP, hence that's also gonna increase our velocity. And finally, we also have our D. So basically, we can find a way to somehow increase the amount of distance that the smoke particle travels before hitting the left plate. And I mean the main ones you should say is increasing the voltage, decreasing the distance between the plate, and increasing the charge. Those are the main 3 ones that we should be looking into. So for this question, just stating 2 changes. Okay, so we can say voltage increase. We can also say that distance between the plate decrease. Distance between plate decrease. Or we can say that that we can increase the charge of this particle. And just by getting 2 of these, you should be able to get simply just achieve grades. Should be achieve questions here. Alright, so for one of these changes, clearly explain the relevant physics of how the change increases the velocity of the negatively charged smoke particle. Alright, so as we were saying before, for example, if we're increasing the voltage, that means it's also going to increase the electric field strength. And by increasing the electric field strength, because EP is equal to EQD, and Q and the D we assume is constant, then EP is proportional to E, and therefore because it's proportional and EP increases, that means that because the E increases, the EP will also increase. And because EP equals to EK, if EP increases, EK increases. That's pretty self-explanatory. And EK is equal to half mv squared. We assume that the mass stays constant, and because the EK is increased, that means our velocity also has to increase. That's for voltage. If we say we decrease the distance between the 2 plates, you can say that E is inversely proportional to D, and if it's inversely proportional, then if its inverse is proportional. If we decrease the distance between the plates, then we can increase the E, and that goes back to our theory of EP equals to EQD, and that's going to link to our increase of the voltage. For increasing the charge, increase the charge, so we know that we also know that F equals to EQ, okay? So we know that F equals to EQ. If we're increasing the charge here, if we increase the charge, and we're just going to assume that the electric field strength stays the same, that means that the force experienced by that particle, so force experienced by that particle, will increase. So that goes up. And because the force increases, okay, we're going to go back to Newton's first law. So basically, if we're experiencing a greater external force, then the change of state of motion of that object will be greater. So basically, this force is going to result in a bigger acceleration. So F equals to ma. We know that the force is increased, the mass stays the same, so that means acceleration has to increase. And acceleration directly links to A equals to V over T. And by increasing acceleration, then the velocity will also increase by the time it hits the plate. And that's basically for this question. You can talk about any of one of those three. One of those three ways. Okay, so I'm just going to do an example. So for example, if we're going to say electric field strength, for example, if we're going to say increasing the voltage. So if we increased, that's terrible handwriting. Oh, that's terrible, sorry. Do not condone this handwriting. If we increase the voltage supply, because E equals to V over D, E will be proportional to V. Sorry, EP is proportional to E, hence EP will increase. EP equals to EK, hence EK. Hence the V increases. So that would basically be an example, one example response to this question. And assuming that it's a good response, then I'm thinking, because these three parts are just all connected, but if we get a good explanation here, then should be looking at somewhere of a merit grade, okay? Confidently a good merit grade here for good explanation. I'm just going to rub this out because I won't have space for the next question. Discuss what could be done with the magnet to affect the motion of the negatively charged smoke particle. Alright, so what do we need to do with the magnet to affect the motion of the negatively charged smoke particle? Alright, so as you can see right now, the bar magnet is basically parallel, in other words, parallel to the motion of the smoke particle. So basically, if it's parallel, then it's not cutting. It's basically it's not cutting the electric field. What am I trying to say? So basically, in order for the most force to be generated, the most magnetic force to be experienced, the magnetic field lines need to be cutting needs to be cutting the current basically, because right now we have our electric field lines that are going from left to right, left to right, left to right. Right now it's the bar magnet is parallel to these lines, so therefore it's going to have little to no effect on the force. So basically, if we want to have the maximum effect on that smoke particle, we do need to turn it so that it's perpendicular to those electric lines. So basically, if we turn it like this, then it's gonna have experiencing the most magnetic force, because it is cutting the magnetic field lines are cutting the electric field lines basically. So basically, to answer this question, you can say that discuss what could be done. So you can say we should turn the magnet 90 degrees so that it is cutting the so that the magnetic field lines, so that are cutting the as right now it's parallel to the electric field lines. Have no effect. So basically, by turning the magnet, we are we're increasing the magnetic force on the particle. Yeah, that should be enough actually. To affect the motion, so hence F equals to ma. So if there is an external force, then an acceleration will take place. Okay, and that will be should be your final answer for this question. So basically, we should turn the magnet 90 degrees so that the magnetic field lines are cutting the electric field lines. Right now, the magnetic field lines are parallel to the electric field lines, so there's no effect, little to no effect. So by turning the magnet, we are increasing the magnetic force on the particle, and because F equals to ma, so basically linking to Newton's first law, if we apply the external force, there's going to be an acceleration experienced by that smoke particle. And saying this, I should give you an excellence grade for this question. And yes, that should be the grading for this question. So you should be getting an excellence grade if you can state. So you have to state that it needs to be turned 90 degrees. And you need to say that right now it has no effect. And you need to explain in terms of F equals to ma. And linking it to the acceleration. And linking all of these bullet points will get you your excellence grade here. Alright, question 2, the ammeter. The diagram below shows a simplified version of the inside of an analog ammeter. Current passes through the coil ABCDE within a magnetic field, causing a magnetic force that moves the needle, indicating the amount of current passing through the meter. A current of 2.5 amps passes anti-clockwise through the ammeter ABCDE. State the direction of the force, if any, on each section of the wire. So AB would be this part of the wire here, and we're going to be using our right hand slap rule. So our thumb is going to be pointing in the direction of the current. In this case, it's going to be pointing in the direction from A to B, because our current is traveling from A to B. So our thumb is going to be pointing in the A to B direction, and our fingers are going to be pointing in the direction of the magnetic field lines. Magnetic field lines always move from the North Pole to the South Pole. So our magnetic field lines should be going in this direction, north to south. So that's where your fingers, so basically your thumb should be pointing in this direction. Your fingers should be pointing in this direction. So basically thumb in that direction, fingers in this direction, and you should see that as a result that your palm is facing downwards. So your palm represents the force and it's pointing downwards. So therefore for the YAB, our force experience will be downwards. Alright, so for the YBC, let me just get rid of this real quick. So YBC, that's this part here. And as you can see that YBC, that's parallel to the magnetic field lines. So once again, the magnetic field lines going like this, north to south. As you can see, the YBC is parallel to that magnetic field lines. So because it's parallel, then this actually cannot be a force experience. So for BC, we're going to write down this is going to be no force. For DE, okay, so once again, we're going to be using our right-hand slap rule. Our current is going to be moving from D to E here, and our magnetic field lines will not change. It's still going to be going from in this direction. So your thumb should be pointing in the direction of the current. That's this way. So that's your current, and your magnetic field lines, your finger should be pointing in the same direction. So basically, it should be the exact opposite of AB. So you should see that the force experience would be upwards in this case. And that will be your final answer to these 3 questions. And this is actually a merit level question. That's pretty generous. This is a merit level question if you get all 3. So all 3, that's a merit question. And if you get 2 out of 3, that would be an achieve level question. Achieve marks. A total force of 0.6 newtons is produced on the wire within the ammeter when 2.5 amps is passed through its coil. Calculate the effective length of the coiled wire between points A and B. The magnetic field strength is 0.2 Teslas. Alright, so we know that our magnetic field strength is 0.2 Tesla. We know that our force equals to 0.6 newtons, and we know that our current is equal to 2.5 amps. And we're trying to find our length. So if you look on your formula sheet, we're going to be using the relationship between F equals to BIL. We have 3 of the 4 variables, so we can use it to find the 4th variable. So 0.6 should equal to 0.2, which is our magnetic field strength, multiplied by our current, which is 2.5, multiplied by the L we don't know. And if we rearrange the equation and solve, we should get that our length should be coming out to be should come out to be L equals to 1.2 meters. So that should be coil wire. Yeah, 0.6. Total force experience. The effective length of the coil wire between A and B. Okay, I think what this question is saying is that this entire thing is 1. No, that's not right. Either 1.2 between A and B. Oh, the total force of sorry, I misread the question. Total force of 0.6 newtons. So that's the force experienced by DE and AB. Okay, that's both. Okay, so basically, if it's both, they're both. Basically, it's both going to be producing the exact same. So it's just going to be 0.3 newtons experienced by each. So instead, we're going to be using 0.3 here. Would be the right answer. And you should get as a result that L equals to 0.6 meters. And that should give you your merit grade for 0.6. And to get an achieved grade, you get 1.2 basically. 1.2 is 1.2 meters is an achieved. Sorry, I didn't quite read the question there. So it says the total force of 0.6 newtons. So that's the force experienced by DE and AB. So AB experiences 0.3 newtons and DE will experience 0.3 newtons. Apologies for that. Alright, so at a later time, a metal rod is moved downwards between the poles of a horseshoe magnet at a constant speed of 7.5 meters per second across a strong 3.5 Tesla magnetic field. The rod AB is 0.32 meters and the sides of the horseshoe magnet are 0.16 meters wide. Calculate the voltage induced in rod AB and state which end is positive. Alright, so this question we're going to be using the relationship of V equals to BVL. We know that our velocity equals to 7.5 meters per second, our magnetic field strength is 3.5 Tesla, and we also know that our length is the length of the conductor inside the magnetic field. So we know that although this is 0.132 meters long, we only count the 0.16 that's inside the field, okay? So when you're seeing questions like this, always pick the length that is smaller, always pick the smaller length, okay, as the value you use. So L equals to 1.6 meters here. Alright, so V equals to 3.5 times of the velocity, 7.5 times of 0.16. And you should get that your that your voltage is 4.2 volts. Alright, so we need to state which end is positive. So in this case, we're going to be using our backhand step rule. So your back of your palm is going to be pointing in the direction of the movement, and this direction is going to be downwards, okay? So your palm is facing downwards. Not palm, but your back side of your palm is going to be facing downwards. And once again, our fingers are going to be pointing in the direction of the magnetic field lines. Magnetic field lines are this way. So our fingers are pointing in the left direction. And you should see that your as a result that this Alright, so your thumb is going to be pointing in the direction of the current, okay? So basically we should see that... Okay, it's really hard to explain without being in person, but end A should be positive. Because, how do I explain this without... Yeah, sorry guys, it's pretty difficult to explain without being in person, but if you use your your backhand step rule correctly, you should find that end A is positive. Alright, so Sam completed the experiment 3 more times, maintaining the same speed and magnet. In the experiments below, he attached the conducting wire with non-zero resistance through a sensitive ammeter, wanting to determine which experiment will induce a current. Experiment 1. Rod AB moves downward inside the magnetic field, wires AD and BC complete the circuit outside the magnetic field. Experiment 2. Rod AB and wire AE both move downwards inside the magnetic field. Wires BC and ED complete the circuit outside the magnetic field. Experiment 3. Rod AB moves downward inside the magnetic field, wires EF remain stationary inside the magnetic field, wires BC, AF, and ED complete the circuit outside the magnetic field. For experiments 2 and 3, state whether a voltage is induced in the wire AB. For experiment 2, as you can see, both our conductors are moving downwards, and that means it has a velocity. It's also inside the magnetic field, so it also has a magnetic field strength, and it also has the length inside the magnetic field. So therefore, it has all the requirements to induce a voltage. So for experiment 2, yes, there is a voltage. For experiment 3, once again, our AE is moving downwards and has velocity, there's a magnetic field, and there's also length inside the magnetic field. So therefore, experiment 3 would also induce a current. So both of these would be yes, and that's your achieved. Yes, achieved should be achieved question here. Alright, so for each of the experiments, justify whether a current flows through the closed loops, explaining the underlying physics principles involved. Experiment 1. Okay, so experiment 1, this rod AB is moving downwards. That's going to induce a voltage. Okay, so that's inducing a voltage, okay, and that voltage is going to, that voltage means it's going to act like a battery. And this is also in a closed loop, so this is a whole thing that's a closed loop, so therefore there will be a current induced, okay? And in order to find where the current is induced, we're going to be using our, once again, we'll be using our backhand slap rule. So our rod is moving down, and our magnetic field lines are moving to the left. And that's where our fingers are going to point, okay? So, so basically, if you do this backhand slap rule, we should see that the so let's just see that the thumb is pointing so thumb should be pointing in this direction. So if the thumb is pointing in this direction, then therefore the current is going to be flowing in the clockwise direction here. So it's going to be like this, clockwise. And that would be a clockwise. For experiment 2, your AB and your wire AE are both moving downwards. Alright, so they're both moving downwards, so it's going to inducing a voltage. So it's going to act like a battery. Once again, it induces the voltage. However, for the current, if you look at the rod AB using the backhand slap rule, we should see that the current is moving in the clockwise direction. However, that's the exact same for the wire, and the wire is going to be moving in this direction also. However, as you can see, when this current comes to here and this current comes to here, they're going to be acting in opposite directions. So because the same amount of wire is inside the magnetic field and the magnetic field stays constant, the velocity is a constant, then therefore both voltages induced are the same. So voltage is the same, induced is the same. Okay, and because they cancel out, they're going to act in opposite directions, they're going to cancel out. So therefore there's going to be no current that flows through experiment 2, and that's because, once again, I was saying the current cancels out. For experiment 3, we have AB moving down and AE remaining stationary. Once again, there's going to be a voltage induced in AB. It's going to act like a battery. And by using our backhand slap rule, we should see that once again our current should be flowing in that clockwise direction. However, there's no voltage induced by AE, no voltage induced, and that's because it's not moving. So we know that V equals to BVL. We know that the velocity is 0, so therefore our voltage induced must be 0. So therefore wire AE equals 0 volts. So therefore it doesn't affect the current of AB. So therefore for experiment 3, because it's a closed loop and there's no opposing currents, then yes, there is current. Alright, that's basically going to be a summary of those events. So for experiment 1, was sorry, I forgot what experiment 1. Experiment 1 was, okay, so rod AB moving and everything else is outside. Okay, so basically I'm going to say that a rod AB induces a induces a voltage by moving in the magnetic field. So rod AB induces a voltage that's moving in the magnetic field, hence it acts like a battery. I can say wire AE does not induce a voltage because it is not inside the magnetic field. You can say that because it is a closed loop, hence current can flow. And don't forget to mention the direction. Current can flow in the clockwise direction. And that's basically going to be your answer to experiment number 1. Experiment number 2, we're going to say that rod AB once again induces a current, induces a voltage. However, AE also induces a voltage. I can't spell, wow. Using right hand side rule, it is seen that both of these provide current. So basically for rod AB, current is in the clockwise direction. But for the AE, it is anti-clockwise. The current is equal magnitude, is equal size, therefore they cancel out. And no current flows. Alright, so for experiment 3, I'm going to say that AB induces a voltage, but AE does not, because it is not moving inside. It is not moving inside the magnetic field. Hence AB acts like a battery, hence there is a closed loop, hence the current can flow. And once again, that's in the clockwise direction. And this would be an excellence level question here, definitely. Excellence level for all 3 experiments linked, both rod AB and rod AE in terms of voltage induced, and getting all of the current and correct direction of the current and the reason why the current is induced. And that will, everything linking together will get you an excellence grade there. Alright, so I'm going to cover up question 3 in a separate video because I'm afraid that my screen recording might cut off after a while. So thank you for watching this video, and I hope to see you all in question 3.